Hi all, welcome back. We are in Chapter P. It's actually in the last section of Chapter P. And technically, this is a bonus section because it's not actually in your book, but it is still important, so we still need to talk about it. We're going to be talking about continuous random variables. So far, we've really only talked about discrete random variables. We found PMFs, we used them to calculate probabilities, and we discussed a special discrete distribution called the binomial distribution. So now we're going to talk about the continuous equivalent to a PMF, and we're going to talk about a few well-defined continuous distributions. First up is, instead of a PMF, we now have a PDF, or probability density function. The important thing to know here is what a probability density function does not represent. It does not represent the probability at a point. So lowercase f of x does not represent the probability that x is equal to a specific number. What does it represent? Well, we don't need to get into that. We just need to remember what it does not represent. And we will remind you of that in a few slides, so very important. I did mention lowercase f of x, so it still gets the same notation as the PMF. That's a little confusing, but that's how it is. And what we really need to focus on isn't the interpretation or the definition. We want to focus on how we use it. So the big idea here in this section is that probability is now area under a curve. So the probability that x is between a and b is the integral of f of x from a to b. So you've probably been wondering, why on earth does this class have a calculus prerequisite? You now know. So we will be doing some calculus in this chapter, mainly just power rule and derivatives of e to the x, but if it's been a while and you feel like you need a refresher, there's something to work on. So like I said, big idea here, probability is area under the curve. There's a couple properties of PDFs. F of x has to be greater than or equal to 0 for all x, so your PDF cannot be negative. If you integrated your PDF from negative infinity to infinity, you would get 1, and that's the idea that total probability has to equal 1. It does not represent probability at a point. Notice I put 3 exclamation points there. It's a really common mistake. So it does not represent probability at a point. In fact, there is no probability at a point. And so that leads us to the next property, which is that the probability that x is between a and b inclusive is the same as the probability that x is between a and b exclusive. So that wasn't true in the discrete case. Being less than or equal to 3 and being less than 3 are two different things. But here, it's the same because, like I said, there's no probability at a point. And the reason for that is, if we think about probability, I said it's area under a curve. How much area is there at one point? There's no area, right? So no area, no probability. So there's no probability at a point. We can do an example. The direction of an imperfection, that should say, with respect to a reference line on a circular object, like a tire, a brake rotor, or a flywheel, is subject to uncertainty. Consider the reference line connecting the valve stem on a tire to the center point. Let x be the angle measured clockwise to the location of the imperfection. You'll notice in this chapter, I'll have a lot of engineering examples. The last time I taught this, I was teaching engineering stats, and I think these examples are kind of fun. So one possible PDF of x is given by this. So it's a piecewise function. If x is between 0 and 360, then f of x is 1 over 360. Anywhere else, it's 0. So that's how you interpret that. Graph the PDF. That's our first step. We want to graph this one. Well, there's what it was, just to remind us. It's pretty easy. From 0 to 360, it is a straight line at 1 over 360. Everywhere else, it is 0. now we can want to find some probabilities. So find the probability that the angle of occurrence is within 90 degrees of the reference line. First step is any good probability starts with a probability statement. So translating from words to symbols, being within 90 degrees is that x is between 0 and 90 inclusive. And again, inclusive versus exclusive, not a big deal here, but it is good practice to write it like that anyway. Even though it doesn't make a difference in the continuous world, it does make a difference when we go back into the discrete world, so we just want to be careful the whole time. And that is equal to the integral of f of x from 0 to 90. So from 0 to 90 of 1 over 360 dx. That integral, the antiderivative, is 1 over 360 times x, simple power rule, and that's evaluated from 0 to 90, so doing that evaluation, 1 over 360 times 90 minus 1 over 360 times 0 gets us 90 over 360, or 1/4. And this was an example of one of our special well-defined distributions. So a continuous random variable is said to have a uniform distribution on the interval from a to b if the PDF looks like this. So ours was uniform on the interval 0 to 360 because it was 1 over 360 there and 0 everywhere else. This is important to recognize because sometimes questions might say, you know, the random variable x has a uniform distribution on the interval 0 to 5. Find a probability. So they might not give you the PDF explicitly, they might tell you information that will allow you to write the PDF. And the uniform distribution is special because if we go back a slide here, when we graphed this PDF, we saw it was just a straight line. So we did some calculus to find the probabilities. The uniform distribution is a special case where you don't necessarily have to do the calculus. You could have just done some basic geometry because the area under the curve, they're going to be rectangles. But other distributions will make us do calculus, so again, good practice. There's also something called the exponential distribution, and a continuous random variable x is said to have an exponential distribution with rate parameter lambda if the PDF is lambda times e to the negative lambda anytime x is not negative. Here, just a word of caution, if you like to look at other resources, that's great, great to get some extra practice, but there's more than one exponential distribution. Sometimes this is written in terms of betas, and it is different, so just be aware which one you're dealing with. Don't get confused, or if you're writing your note card for an exam, make sure this is the one on your note card. So we'll do another example, this time with the exponential distribution. So the time it takes a reference librarian to locate a book is exponentially distributed with lambda equal 0.05. Cool, so here's a perfect example of where I said it won't give you the PDF, that's your job. So that's our first task, write the PDF. Well, from the last slide, we know that this is going to be 0.05 times e to the negative 0.05x, anytime x is not negative. 0 everywhere else. Great. We have a PDF. I'm just going to keep the example up there for reference. Now that we've got a PDF, calculate the probability that x is less than or equal to 20. Okay, well, first off, probability statement. It was already given to us, but we should still write it. So probability that x was less than or equal to 20 is equal to the integral from 0 to 20. So the lower bound here is 0 because that was the lowest possible x value we could have based on our PDF. So from 0 to 20 of 0.05 times e to the negative 0.05x times dx. And evaluating that, again, not too hard. This is maybe a little more complicated than the power rule, but it's just a simple little chain rule. We get that this is e to the negative 0.05x evaluated at 0 and 20. So Because of that negative out front, normally it would be, evaluated at 20, subtract off evaluating at 0. Because of those negatives, we're going to flip things. So that's why that happened in the next line here. So e to the negative 0.05 times 0 minus e to the negative 0.05 times 20. And that gets you 0.6321. Okay. Ooh, find the cutoff for the 5% fastest times. I'm going to work backwards here. So this time you weren't given an x value, you were given a probability. So in the last question, I gave you an x, I wanted a probability. Now I gave you a probability, I want an x. So we know 5% fastest, pause and think about this, that means small numbers, right? Being faster means it takes you less time. So this 5% is in the left tail of our distribution. So 0.05 is equal to the integral from 0 to some number k of 0.05 e to the negative 0.05x dx. Sorry about that. I think I kept copy and pasting the same LaTeX, so that's going to be in each of these slides. So, again, same thing, evaluate it down. Now we have this placeholder k, so we get down to 1 minus e to the negative 0.05 k is equal to 0.05. Great, but we want k by itself. So let's do some manipulation there. I'll subtract 1 from both sides, and then I'll divide by negative 1 on both sides. Then I take the natural log of both sides because that's how you cancel out an e. And then I divide by negative 0.05, and I get down to 1.02. We can also find means and variances. So we have formulas for this that's the continuous analog of the last formula. So here, the mean of a continuous random variable is the integral from negative infinity to infinity sorry about this. Just gonna fix this real time and not re-record this. So the mean is the integral from negative infinity to infinity of x times f of x dx. The variance is the integral from negative infinity to infinity of x minus mu squared times f of x dx, and we have a shortcut formula. So instead you could take the integral from negative infinity to infinity of x squared times f of x dx, and then subtract off mu squared. And just like last time, third one might be easier to work with. So for an example, we're going to let x be a continuous random variable with this PDF. Now that PDF has a c in it, so our first goal is find that constant c that will make f of x a valid PDF. Well, being a valid PDF means the total probability needs to integrate to 1. Did it again. I am sorry. So, using the fact that the total probability needs to be 1, we know that the integral from negative infinity to infinity of cx squared dx is going to be 1. But we know that we don't care about negative infinity to infinity because it's 0 for a lot of those. The only places where ours isn't 0 is when the absolute value of x is less than 1. That means when x is between negative 1 and 1. So we can update our bounds. And then I can pull the constant out front. So cx squared dx, I can move that c out front of the integral. The antiderivative of x squared is 1/3 x cubed. And then I'm going to evaluate from negative 1 to 1. So c times 1/3 times 1 cubed minus 1/3 times negative 1 cubed, and we end up with 2/3 times c is equal to 1. So 2/3 c is equal to 1, that means c is equal to 3/2. So we have found a value of c that will make this a valid PDF. And again, I'm going over the calculus a little bit here as I go, so this might be way too many steps for some of you and might not be enough steps for others. If you fall into this isn't enough steps group, feel free to email me or set up an office hours appointment. I won't spend too much time on it in the slides because it is a prereq for the course, but I am more than happy to talk about calculus in office hours. Just let me know. So, okay, we've got our PDF. We also now have that value of c. Find the mean of x. Well, negative infinity to infinity integral from negative infinity to infinity of x times f of x dx. That's what we start with. Now let's fill in the pieces. Our bounds are only negative 1 to 1, and our f of x is 3/2 x squared. So pull that 3/2 out front and combine the x's. You get 3/2 times the integral of from negative 1 to 1 of x cubed dx. Antiderivative of x cubed is 1/4 x to the 4th. So then do some evaluation, and you get that the mean is 0. And that can happen. Sometimes that seems weird, like maybe something went wrong. And it's okay. Means can be 0. In fact, there's going to be a very famous distribution we're going to use a lot that has a mean of 0. Okay, let's find a probability too, just for more practice. Find the probability that x is greater than 1/2. So, what are our bounds? It's important to think about. Well, we know that x goes from negative 1 to 1, so being greater than 1/2 means being between 1/2 and 1. So we set up our bounds like so. And then again, pull that 3/2 out in front. Antiderivative of x squared is 1/3 x cubed. Do some evaluation. You get 7 out of 16. And that brings us to the end of the continuous distributions chapter. So that was pretty quick, because really it was just repurposing the calculus knowledge that we already know to find probabilities. So I'll post some questions where you can work on this on your own, and let me know if you have any questions.